This apparently is the world's biggest focal pendulum. Look it up. I think it's F-O-C-O-U-L-T. And it tells the time by, it's a big pendulum that's driven, but it tells the time by the Earth spinning underneath it. And obviously that stays in the same place. So it shows the Earth's rotation. And it's here.
Very simple things, like you go back to the Greeks, so Aristotle and the great, very clever people, but they thought the Earth was at the centre of the universe. Why? Because it feels like it's at the centre of the universe. It feels like we're not moving, and that's quite a deep point actually in physics. It's like, why is it that we're flying around relative to the sun very fast at whatever speed it is, 18 miles a second or something like that, and the whole solar system is going around the Milky Way galaxy and so on? But why is it that we don't feel it? And the Greeks quite naturally said, well, because we're at the centre of the universe. They also said everything falls towards the Earth, so therefore the Earth must be at the centre. It's natural.
Right.
And actually it's quite a deep thought to understand why it doesn't feel that we're moving. You have to go all the way to Einstein, really, for someone to take that very seriously. And he said, well, this... there's a great little explanation in Stephen Hawking's Brief History of Time about this, that the idea that you can't tell whether you're moving or not demolishes the notion of absolute space.
That's essentially what's happening when you're on a plane. I mean, if you're throwing a ball up in the air and catching it on the plane, it's happening at a much smaller scale, right?
Yeah. I mean, you're flying at whatever, 600 miles an hour relative to the ground.
But it doesn't seem like it when you're sitting there.
Yeah, and Einstein elevated that to a principle and said, if you're moving at if you're not accelerating, you're just moving at a constant speed in a plane, or now. I mean, that's essentially what we're doing now. We're moving around the sun at effectively constant speed. Then you can't tell. So there's no experiment you can do. We could look at the decay of a radioactive nucleus or some electricity and magnetism or bounce a ball, have a pendulum, whatever it is. And there's no experiment you can do to tell you whether you're moving or not. Therefore, that concept has no meaning, because you can't measure it. And that's led Einstein to relativity.
Wow.
So that's the basis of general relativity, which is our best theory of the universe.
Exactly. They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down. Gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this. The reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the Earth. So he concluded they weren't. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the Earth. So he concluded they weren't. The first planet I'm travelling to is Neptune. Its gravity is just fractionally stronger than here on Earth. This is the gravitational field on Neptune, and you feel, you know what, I could probably get used to this. I could probably live on the surface of Neptune.
Can you lift your hands a little?
There we go.
Yeah, and down?
And it is actually quite an effort. It is noticeably heavier. It's like having a reasonably heavy weight in your hand.
You ready to go to 2.5G?
Yes, and I will move from Neptune to Jupiter.
Let's go there.
Jupiter is over 1,300 times more massive than the Earth, but because it's mostly gas, it's not very dense, so its gravity is just over twice as strong at its surface. Well, now actually it is quite difficult to lift my hand, and that's 2.5 G. I wouldn't want to sit here for half an hour.
And can you lift both of your hands above your head? See what happens there.
Let's see. So actually, just about, but actually it's an immense amount of hard work. So it would be hard work living on Jupiter.
Let's go to 4G.
Actually, this is heading to a planet around a planet called Ogle 2 TR L9b, which is around a star in the constellation of Carina. It's one of the exoplanets we've discovered. Oh, and there we go. Now that is actually beginning to feel quite unpleasant.
Can you describe what you're feeling?
A very heavy face.
All right.
My head is extremely heavy.
How about your lungs? Inhaling, exhaling, breathing?
It's much harder work. I can't lift my hand off my leg.
Okay.
And that's at 4G.
Yeah.
But my head and my face feel very, very heavy.
Yeah.
It's quite an unpleasant feeling.
We'll go to 5 and let me know if you have any visual disturbances.
I'm now en route to a newly discovered exoplanet, WASP-8b. 4.4. This world sits in the small and faint constellation of Sculptor. Quite hard to speak. It has a gravitational force nearly 5 times that of the Earth.
All right, we'll go to 5G.
Oh, very foggy.
Okay.
Very foggy.
Very foggy. Still foggy?
Yeah.
All right.
Take it down.
Okay, we'll take you down.